All right, so what we did last time where we ended is we were in section 3.3, the word problem section. We did on the sheet that I handed out, we did the first 4 problems. So as I told my other class, on the test that you have on Tuesday next week, I'm just going to put one of each of the different styles of problems. So there's 3 styles of word problems. There's the perimeter problems we did, and we made systems out of. There was the, if you had different price tickets, and then there's today's problem. So that's where we're going to start. We're going to do the next 2 problems on that sheet. We're not going to do example 7, so don't worry about it. Okay, we're going to end with what's called a mixture problem. And we're going to each do an example of this. And we're going to set up the system, and then we're going to go on from there. And then after that, there's the syllabus says 2 sections, 4.1, 4.2, but the old version of the book, it was all 1 section, and then they split it apart so they could sell more books, because that's the way that industry operates. So it's not going to be a super long amount of stuff. So then we'll be at the point that we need to be, so we can take that test Tuesday. So anybody need one of these? You forget yours, need another? You just want me to autograph one because you want my souvenir? That'd be great. Yeah. We are going to do 4.1, 4.2. I was just letting you know that it wasn't going to be an overwhelming amount of information, because it sounds like 2 sections. Oh my gosh, we're going to have to rush, but it's not going to be a rush. It wasn't a rush yesterday in my other class. So, and you guys, for what I don't know why, we tend to move quicker than that class. And I forgot all my pens. Okay, so here we go. On that sheet, example 5. So again, if you're watching the video, you can print this out. It's attached as a PDF in your Canvas. So what we're going to do, and this is an important problem for a couple reasons. If your destiny is taking you to any sort of science field, which I'm assuming since you're in the intermediate algebra, you're in the STEM pathway, you're going to see this. You're going to deal with mixture problems in some science class. So it's important for that. So what we're going to do in example 5 is our last type of word problem we're going to deal with, which is called the mixture problem. So in general, what this presents us with is a situation where I have 2 different, whether it's chemicals or prices or any sort of situation that you have 2 different concentrations, and you want to mix them together to create a new concentration for whatever purpose that you have. We're going to also see these mixture problems again when you take college algebra with me or somebody else. This is one of the word problems that we reinforce in that environment. So let's read through the problem, and then before we do it, I want to remind us how percents work. So it says, how many ounces each of a 5% hydrochloric acid and a 20% hydrochloric acid, so we have 2 different concentrations, how much of each must be combined to get 10 ounces? So for whatever project I'm doing, I need just a little vat of 10 ounces of a 12.5% solution. So first off, in case you don't remember your chemistry from high school, the way acids or some of the problems in the book deal with alcohols, the way those work in chemistry is your acid molecules are floating around in water. Okay, so the stronger the acid, the more acid molecules, the higher percentage there is. And so for whatever purpose, I need a 12.5% solution. Okay, before we do that, let's remind ourselves, because I find sometimes students don't feel comfortable working with percents. If you need a full review of how to work with percents, either email me or see me after class. I have some videos that I can give you for that purpose. But let's pretend after class you are super thirsty. So you run to the convenience store and you buy a bottle of grape juice, okay, because you love grape juice. Okay, so you go to the store, you're buying yourself a nice big cold bottle of grape juice. And as you're walking up to the register, you realize, okay, you have bought 100 ounces of grape juice. Okay, nice round number. While you're waiting in line to pay, though, here's what you see on the label. You see that you haven't really bought a whole bottle of grape juice. What you bought is something that is 35% juice. I don't know what the other amount is. I'm not going to even hypothesize. It's probably disgusting, but it's 35% juice. So here's my question to you. If I just want to know out of my 100 ounces, so the bottle we're assuming is full, I want to know out of my 100 ounces, if it's 35% juice, how many ounces of juice do I actually have? Not a super hard question, but I just want to remind us how percents work. Does anyone know, anyone remember how we can figure out how many ounces of actual juice molecules are floating around in this bottle? How can I figure that out? I'm sorry? That's a great first step. We can't work with a percent with this. A percent is just a ratio. It's telling you percent, the word per means divide, cent means 100. It's just telling you the ratio of how many parts out of 100. So 35% means 35 parts out of 100. When we turn it into a decimal, it's 0.35. You always move the decimal 2 places left. Hopefully you remember that. But I can't just, that's not the answer. Percents don't work alone. If you walk into a store with a 25% off coupon, that coupon has no value till you actually buy something. So what now do I do with that percent to figure out how much juice is in my bottle? I'm sorry, what did you say? Not over 100. I've already done that. That's why I moved the decimal. Okay, that's a good thought. But I have to do something with this 100 ounces. Yes, thank you. Good. I know we're shy here first thing in the morning. What I'm going to do is I'm going to multiply it by the 100 ounces of liquid. This is now going to tell me how much juice is actually in the bottle, and the rest is all sorts of other stuff. So 0.35 times 100 is 35 ounces of juice. That's how percents work. Percents never work by themselves. It's always a percent of something, and I have to multiply in order to figure that out. So in my little example here, when I have 5% hydrochloric acid, it's 5% of however much volume I have is actually the acid molecules. That's how this works. Okay, so back to our problem then. I want to figure out how much of each of these two things that I have to combine into a beaker in order to get my 10 ounces. So whether it's this class, whether it's the next class, here's how I like to set up my percent problem or my mixture problems. It helps me think about it. If this doesn't help you at all, then you can just write down the equation. So I like to do this. Here is my first mixture. This is my 5% mixture right here. And I'm pouring it into a bowl with my other mixture. This is my 20% right here. And I'm ending up with a 12.5% mixture. So all I've done is, instead of bottles, because I'm really not that good of an artist, I don't know if you can tell, I can barely draw. Boxes work easier for me. So each of these boxes represents what I'm adding in. I have a certain amount of the 5% plus a certain amount of the 20%, and my result is what I want it to equal is a certain amount of the 12.5%. That's all I've done is label the situation with these boxes. Are you tracking with me so far? I know these are difficult problems. I understand word problems are very strenuous. Okay, so if you have a question, please interact with me over this. So now what we're going to do is we're going to label two things because we need two equations. We're using system of equations to solve problems. The first equation, what I'm going to do up at the top is I'm going to label the total amount of liquid. Okay, what's the total volume that I am adding in? Okay, well, here goes. In the problem, in those two sentences we are given, are we told how many ounces of 5% we're throwing into the bowl? No, so let's call that X. And you might say, how did you know that, Perkster? Well, the first words say how many ounces. How many? That's a question. I don't know. Okay, so how many ounces each of these two things? So since it says each, do I know how many ounces of the 20% I'm putting into my container? No, so I'm going to call that Y, because they're going to be different. I don't know. It's not going to be equal amounts necessarily. According to the problem, though, am I told how much I want as a result? How much total I want? How much? Okay, I want 10 ounces. And for whatever reason, the abbreviation, in case you didn't know, the abbreviation for ounces is OZ. So not the Wizard of Oz there, it's just OZ, ounces. So far, so good. Do you understand where each of these labels came from? Is there a question? Because I'm going to have you do example 6, which is almost identical to this, just different numbers that you have to plod through. All right, well, the second thing, since I have two variables, I have two things I don't know, I need two equations. Okay. Someday when we take college algebra, we'll have systems with three unknowns. You need three equations to figure those out. Okay, so, but we're getting ahead of myself. I'm excited for it. So this is how percents work. This is the total amount of liquid. So now what I'm going to do below the box is I'm going to say, okay, what's the total amount of acid or alcohol or juice or whatever the particular problem is asking you to find. Well, that's why I did the quick reminder with our grape juice when we were thirsty, is this. If this box is filled with some amount of liquid and 5% of it, so just this little bit right here, this little bit is the amount of acid, how do I figure out the volume of that little bit? What do I do? 5% into a decimal. What's the 5% going to be as a decimal? 0.05. You always move it two decimal places. 0.05. But again, percents never stand alone. It's always a percent of something. So what am I going to multiply this by? Yeah, I don't know how much volume there is. So it's going to be X. Okay, so X. So once I do know the volume, once I figure out X, I can then figure out how much acid is actually in that container. How many acid molecules? You with me so far? I know this is difficult stuff, so don't be shy with me. All right, next one. So again, how much acid? Well, if this box is filled with liquid, the whole thing's full, then 20% of it. So like right here, this is the amount of acid in the box. The rest is water. That's how acid works. When you take your chemistry, you'll learn that. So what's my amount of acid in this box? 0.20 or just 0.2 times Y. I think you said that, so I'm right. I hope it's just not a phantom sound. Now over here, now I know this box here is 10 ounces full. I want my percent to be 12.5, so somewhere right here. So how many acid molecules are in this? How do I calculate that? Perfect, 0.125 times 10, yes, times 10, great. Because that time I do know the volume. The volume's 10 of this one. So each time, the total amount of liquid, that's just how much is in each of these boxes. And then the amount of acid is the part of that. So it's percent times total, percent times total, percent times total each time. And now I have the information to make my two equations. And the top equation is this. I'm just going to read across the top and the bottom of the box. The top equation is the amount of liquid in my first box plus the amount of liquid in my second box has to be equal to 10 ounces. The amount the first box contributes plus the amount the second box contributes has to be 10 ounces. And then the second one says, okay, that's the total amount of liquid. Now we're going to deal with the total number of acid molecules, okay, because that's a part of this. So the total amount of acid molecules the first box contributes plus the total amount of acid molecules the second box contributes has to equal the total amount of acid at the end result, which is 10 times 0.125 or 1.25. There's my system. I'm going to take us one more step. But like I said last time, I'm hoping that you've done the homework from section 3.1 and solving a system of equations is not too big of a deal. Okay, you can use elimination, you can substitution, whatever makes you happy. I wouldn't graph this. That would be kind of a crazy thing to do. The other thing that I want to do is when we got decimals, sometimes that becomes a little funky. I want to make sure that we know where to go next to make this a little easier to look at. And so again, this is just arithmetic. If I want to get rid of the decimals, how many decimal places do I have here? 2. How many decimal places do I have here? 2 the way I've written it, or if you just have 0.2, it's 1, doesn't matter. How many decimal places do I have here? So if I want to get rid of the decimals and have those all be whole numbers, what do I multiply every single term by? Does anyone know? 100. Great. Yes, you've seen this before. Great. I'm glad that this is not super mysterious. 2 decimal places is 100. Now you might be thinking, hey, Kirkster, I have 0.2 for the y. It only has 1 decimal place. Can I just multiply that by 10? And the answer is no. You have to multiply everything by the same thing. So you have to multiply by 100. Okay, so you can't just multiply each term by different things. That changes the equation. So then this is the system that you will solve. You could do this for homework. You can x plus y equals 10. And then 100 times 0.05, your calculator will tell you 100 times 0.05 is 5x. 100 times 0.2 or 0.20 is 20y. And then 100 times 1.25 is 125. And there you go, that's the system. And I would eliminate, personally, that's my favorite method. You don't have to, but what I would do to solve this, my next step is, if I want to eliminate the x's, what would I multiply everything by on this top equation if I want to eliminate the x's? -5. If you're a y person, if you wanted to eliminate the y's, what would you multiply everything by to eliminate the y's? -20. Okay, so then you'd go, you'd smush the equations together, and you'd have your answer. Okay, and you'd know how much of each to go ahead and do. So what I would like you to do is problem 6, our last example from this section. It's a very super similar situation. I would like you to at least set up the system. If you have time, you can keep doodling on it, but go ahead and give you a couple minutes to work example 6. Yeah, okay. All right, I'm going to get started because all I asked you to do is to set the system up. So if you're going further, if you're solving it, that's fantastic. So this setup's very similar. Mixture problems tend to all work the same way once you get the hang of them. So I understand these are difficult. So as you're getting the hang of it, whatever questions you have, let me know. So this question says, how many liters each of a 15% solution and a 25% have to be added, and you want 30 liters of an 18%. So for whatever application, you need 18% solution. So here we go. Let's look at the total amount of liquid that I have. So first, I've got a 15% solution, I've got a 25% solution, and I want to end up with an 18% solution. So there's the basics of it. So how much 15% am I adding? Am I told? Okay, that's going to be X. Great. How much 25% am I adding? Am I told? Yeah, I don't know. It says how much. Those are the things we're figuring out. And then how much of the results do I want to have? I want 30, and this time the units are liters. Okay, that's my total amount of liquid. So this box is going to have X liters, I don't know. This box is going to be filled up with Y liters, again, I don't know. This box, the total amount that once I've poured both together, the total amount is 30 liters. Okay, so that's my first equation, right across the top. X plus Y has to be 30. Now my percents, okay, if this box is filled with however many liters, how much of it is actually acid, the other molecules floating around in the water? 0.15x, great. 15% of it is acid. Okay, if this box is filled with so many liters of acid, and I said 25%, what's this right here? What's the shaded volume going to be? Percents always work the same way. It's a percent of a total, a percent of a total. Okay, percents never stand alone. And then last but not least, if this has 30 liters, and I know 18% of it is actually acid molecules floating around in the water, then what's the volume of the acid molecules? Okay, 0.18 times 30. Okay, percent total. And that gives us our two equations. So the first equation I'm hoping you wrote down is that the amount of volume in the first box plus the amount of volume in the second box has to be equal to 30, because that's what I wanted as my end result. And then the second equation is the percent equation. The number of acid molecules the first box contributes is 15%. The number of acid molecules, the second one, is 25%. And then the third one, 0.18 times 30 is, what is that, 540? 5.4? 5.4? There's your two equations. I'm going to take it one. I did. Thank you. Only you and I noticed that. Everybody else saw why there. Good. Thank you. I'm going to take it one more step again, just to make the numbers a little more manageable. I don't want the decimals. I mean, if you can do the problem with the decimals, super duper. But what am I going to multiply every term of this equation here by to get rid of the decimals? 100 again, because I have two decimal places on those two terms. Have to multiply everything by the same thing. So my top equation, I've not done anything with it. It's ready to rumble. My bottom equation, 100 times 0.15 is 15. 100 times 0.25 is 25. And then 100 times 5.4 is 540. Yeah. Perfect. Yeah. If they said that one of these was like 15.5% and this one was 0.155, you'd do everything by 1,000. Yeah, however many decimal places, that many zeros. Okay, fantastic. And then just last thought before I stop this video, we're done with this section. If I want to eliminate the x's, what am I going to multiply each term of this one by? Negative 15. Perfect. That's solving the system. Great job. Practice those.